Artemis 3 is the first Artemis mission that will land humans on the lunar surface. But this process will not be as simple as we imagine. Due to operational requirements, the crew doesn't fly and land directly from Earth to the Moon's surface in one vehicle. First, the crew launches aboard the SLS rocket and travels to lunar orbit inside the Orion spacecraft, just as in the previous mission. Once in orbit, they dock with SpaceX's Starship HLS, which has been pre-positioned there. This is essentially a dedicated lunar lander designed specifically to take astronauts from orbit down to the surface and back up again. Then, they make a safe descent to the lunar surface using this lander. For Artemis 3, the focus is on the Moon's south pole. This region is important because it contains permanently shadowed craters where water ice may be preserved. It also receives more consistent sunlight on certain elevated areas, which makes it ideal for sustained operations. Once on the surface, astronauts will conduct extravehicular activities. They'll collect samples from different areas, deploy scientific instruments, and document the environment. These samples will be analyzed back on Earth to better understand the Moon's composition, history, and resource potential. The mission will be relatively short, and astronauts will spend a few days on the surface. This is precisely the point at which the success of Artemis 3 determines whether the program can move forward to more ambitious objectives. Gateway Station Assembly. Once Artemis 3 proves that surface operations are feasible, the program shifts focus toward building permanent infrastructure. This is where the lunar space station called Gateway comes in. Artemis 4 will be the first mission to contribute to Gateway's initial operational configuration. This is a small station that will orbit the Moon on a permanent basis, much like its counterpart in Earth orbit. It will serve as a staging point for lunar surface missions and a test bed for deep space operations. During the mission, crew members will deliver and install key modules, ensuring the station is functional and habitable. Unlike the ISS above us, Gateway will orbit the Moon in a highly elliptical path. This orbit allows it to support missions to various locations on the lunar surface while remaining accessible from Earth. Part of the orbit takes Gateway close to the Moon's south pole, ideal for supporting surface missions there. The other part takes it farther out, providing clear line-of-sight communication with Earth. This balance makes the orbit the most efficient one for sustained lunar operations. Following Artemis 4, subsequent missions will continue expanding Gateway. New modules will be added incrementally, each one bringing additional capabilities. These might include enhanced power systems, scientific laboratories, docking ports for visiting spacecraft, and storage for supplies. Gateway serves multiple purposes. It provides a safe haven in case of emergencies during surface missions, ensuring constant contact even when the crew is on the far side of the Moon. It allows crews to spend extended periods in deep space far beyond the protective shield of Earth's magnetosphere. Gateway also enables flexible mission planning. Instead of launching directly from Earth to the lunar surface every time, crews can travel to Gateway, dock, and then transfer to the HLS for descent. It is expected that it will reduce the amount of fuel and equipment that needs to be launched from Earth with each mission, making the program more sustainable and cost-effective. Base Camp Construction. The Artemis Base Camp will allow astronauts to live and work on the Moon for weeks or even months at a time. The construction process is planned to begin with Artemis 5 and continue through Artemis 6 and beyond. During these missions, critical infrastructure components are delivered to the surface piece by piece. Habitat modules where astronauts will live, power generation systems to provide electricity, and rovers for transportation and exploration. The Moon has no atmosphere, so there's no protection from micrometeorites, radiation, or extreme temperature swings. During the lunar day, surface temperatures can reach 260 degrees Fahrenheit. During the lunar night, they drop to -279 degrees. Any structure or system placed on the surface must be able to withstand these conditions. The initial phase focuses on basic survival infrastructure. Habitat modules provide pressurized living space, life support systems, and radiation shielding. These habitats are designed to be modular, meaning additional units can be connected as the base grows. Each module includes sleeping quarters, workspaces, and areas for exercise and recreation. Although this may seem like an environment with more amenities than strictly necessary for a scientific mission, keeping astronauts physically and mentally healthy during long stays is just as important as providing air and water. Power systems are another critical component. Solar panels are the primary source of electricity, but the lunar night lasts 14 days, during which solar power isn't available. To bridge this gap, large batteries or fuel cells are deployed. Some missions may also test small nuclear reactors, which could provide continuous power regardless of day or night. Rovers allow astronauts to travel beyond the immediate landing zone, expanding the area they can explore and study. Modern lunar rovers are larger, faster, and equipped with advanced navigation systems, scientific instruments, and the ability to carry significant cargo. Some are designed to be driven by astronauts, while others operate autonomously, scouting ahead or transporting equipment without human supervision. In-situ resource utilization. This is the concept of using local materials rather than bringing everything from Earth. On the Moon, this primarily means extracting water ice from the soil and producing oxygen from lunar regolith. Although the idea of extracting water from a barren moon with no atmosphere may sound crazy, advancing technology is making it possible. Water ice is believed to exist in permanently shadowed craters near the lunar poles. If this ice can be extracted and purified, it serves multiple purposes. It provides drinking water for astronauts, which is critical for long-duration missions. It can also be split into hydrogen and oxygen through electrolysis. The oxygen is used for breathing, while the hydrogen and oxygen together can be used as rocket propellant. This dramatically reduces the amount of fuel that needs to be launched from Earth, making missions more cost-effective and sustainable. Oxygen can also be extracted directly from lunar regolith, the fine dust and rock that covers the moon's surface. Regolith is rich in metal oxides, and chemical processes can separate the oxygen from the metals. This oxygen can be used for life support or propellant production, while the metals might eventually be used for construction or manufacturing. The implications of a successful ISRU are enormous. It means the moon can support itself to a significant degree, reducing dependence on Earth. It also means the moon can serve as a refueling station for missions heading deeper into the solar system. Instead of launching a Mars-bound spacecraft with all its fuel from Earth, it could refuel at the moon, where producing propellant is far easier due to lower gravity. Routine operations. By Artemis 6 and beyond, the program enters a new phase: routine operations. Gateway is fully functional. Crews arrive at Gateway aboard Orion and then transfer to the HLS for descent to the surface. After completing their surface mission, they return to Gateway and eventually head back to Earth. This cycle becomes repeatable and sustainable. Missions occur more frequently, surface stays get longer, scientific objectives get more ambitious. At the same time, the base camp infrastructure continues to expand. Perhaps at this stage, the moon becomes a place where you work a regular 9 to 5, no longer a deadly exotic destination. It's worth noting that the Gateway to Surface cycle also allows for crew rotations. Instead of sending a single crew to the moon for a short mission and then waiting months or years for the next one, Gateway enables overlapping missions. One crew might be on the surface while another is at Gateway conducting experiments or preparing for their own descent. Commercial resupply missions become part of the routine as well. Cargo spacecraft, potentially operated by commercial partners, deliver food, equipment, scientific instruments, and spare parts to Gateway. From there, supplies are transferred to the surface as needed. This logistics network mirrors the system used to support the ISS, but adapted for the greater distances and harsher conditions of lunar operations. A testbed for Mars. As I mentioned earlier, the moon also serves as a proving ground for Mars. Every system tested on the moon, every lesson learned, every problem solved brings humanity one step closer to sending people to Mars. Long-duration missions at Gateway and on the lunar surface generate critical data on how humans respond to extended periods in deep space. Astronauts there are exposed to cosmic radiation and solar particle events, just as they would be on the way to Mars. While the Moon is only 3 days away, Mars is months away. If something goes wrong on the Moon, a crew can return to Earth relatively quickly. If something goes wrong en route to Mars, there's no quick return option. The ISRU testing on the Moon directly informs how resources might be extracted and used on Mars, where water ice and atmospheric carbon dioxide could be converted into fuel, water, and oxygen. By the time the first crewed mission departs for Mars in the late 2030s, every major system will have been validated on the Moon. Artemis isn't just a return to the Moon. It represents humanity's next step as a spacefaring species, proving we can live and work beyond Earth, not just for days or weeks, but indefinitely. If you liked this video, don't forget to subscribe. I'll see you in the next video.